Flipped classroom video for Maths A2 Unit 3, Concavity. First we're going to look at what concave and convex functions are. What's the difference? Well, you have met them before. We can see a curve of y equals x squared, function y equals x squared on the left, and we have y equals minus x squared on the right, at least the shapes of them. And there's an obvious difference between them, apart from them being upside down in terms of values. The shape of them is upside down compared to each other. So turns out that the x squared is a convex function or convex function, and the minus x squared is a concave function. Now there's a good way of remembering concave, which is that it's the similar shape to if you look at a standard, if you like, cave. So we draw around the edge of the cave and we get a concave function. So we have a cave and a concave function, just to reiterate. Okay, so what's the difference? And it's quite interesting to have a look at the change from convex to concave. So we have a convex function and it's gradually going to change, and we can see it flattening out. So what do we call a function that is neither convex nor concave? And you would have seen as that little video proceeded that we get a straight line between them. Okay, so as I mentioned earlier, or did I mention earlier? Anyway, the point is, on this slide, it can be subtle. So concave doesn't have to actually look like a cave. We can reference the cave idea if we see a curve and have to work out whether it's concave or convex. So if we look at this one, if we were to continue sort of sweeping our pen along that, it would end up looking like a cave, I think. Whereas this one wouldn't. So the right hand one is indeed convex and the left one is concave. Okay, now concavity, which obviously stands for whether it's concave or convex, changes as we travel along functions. Often, not always. You can probably think of one at least in trigonometry where it changes, but this one is actually a polynomial. We don't really care at this point what its formula is or anything, so let's have a look at it. So it starts off, if we look across from the left, as concave. Then we have part of it that's convex, and it changes as we go along. Now we'll have a look at those changes now. So this first bit was concave, and it changes. So the point with the question mark is the point at which it's changing from being concave to being convex. And we can see at the end of the red part that's drawn in that it changes again, becomes concave again, and then becomes convex again. So it can be changing, so we need a way of classifying it that doesn't depend on looking at it and saying whether it looks like a cave or not. And actually, if we look at the first section of this, the brown section, we can see when I start this clip going that the gradient decreases. So just have a watch of this. So the gradient is decreasing and it gets to that point and starts increasing, and that's convex. And then it gets to the blue bit, starts decreasing again, that's concave, and then the orange bit, it increases, which is convex. So if we look along that curve now in place on the axes, if we put dy by dx in, that allows us to think about turning points. So we can see that when dy by dx is 0, we have a maximum at about minus 2.3, and then a minimum at about just over minus 1.3, and then we have a point of inflection, a stationary point of inflection at 0. And the value of dy by dx at each of those points, as you already know, will be 0. Okay, so also dy by dx is decreasing when we're at a maximum, so it changes sign, increasing for the minimum, again changing sign, okay. Now, having a look at these points where the concavity changes, you may notice something straight away in relation to the dy by dx graph that we have. And sure enough, the points where the concavity changes are the points where dy by dx is at a turning point. So for the first change between the brown concave section and the red convex section, we have a minimum for dy by dx. Between the red convex and the blue concave, we have a maximum, and then between the blue and the orange, we have a minimum. But that's for dy by dx. Okay, so when we change from concave to convex, or vice versa, then we get a turning point for dy by dx. Okay, so we'll come back to that when we're looking at what are called points of inflection. You've met stationary points of inflection, but we'll come back to that in another video. For the moment, we'll just have a look at the classification of convex and concave. So it's related to the gradient. So for a turning point, we know that the gradient is 0 and that dy by dx is changing sign. For a convex function, the gradient is decreasing, and for a concave function, the gradient is increasing. For a turning point, what we know is that if we have a maximum or a minimum, then d2y by dx squared will be either negative for a maximum or positive for a minimum. So it is definitely not 0. When a function is convex, then the d2y by dx squared will be negative, reflecting the fact that the gradient is decreasing, whereas for a concave function, d2y by dx squared will be positive, reflecting the fact that the gradient is increasing.